这边有几个 theorem 哦，就是说 let S be a subspace of Rn, then Rn equal to S direct sum S orthogonal, okay? And also dimension S equal plus dimension S orthogonal equal to N, okay? And the S orthogonal equal to S. The first one implies first the second one, right? I mean, if you have like a, because we already show you this one, right? No. Where is it? This one, right? So basically, like not the orthogonal. I mean, previously we have shown like the where is it? The direct sum. Oh, not here. It's direct sum. This one, right? If V is S1, direct sum S2, okay, and V is n-dimensional, then dimension S1 plus dimension S2 equal to n. So basically, like if we can show like if we can show Rn is S direct sum S orthogonal, then dimension S plus dimension S orthogonal obviously will be n, right? From the previous theorem. Okay, so the problem is the first one, right? So let's see. There are many ways to prove that. Okay, one way, I mean, one constructive proof is like this. Okay, so if you have like a orthogonal basis of S, okay, if you have a basis of S, okay, we know the size of this basis must be n, right? Because like we already know it's Rn, right? Okay, so if you have a basis for Rn, okay, the number of vectors in this basis must be n, right? But did we discuss like an orthogonal basis previously? That's my question. For Rn, we know like this is obviously like there must be such a basis exist, right? A number of vectors, okay, which spans Rn, and also like they are independent, right? Okay, we know that. Okay, but did we discuss orthogonal basis or not? No. If no, that's fine. Okay, so if we assume there's an orthogonal basis, that's the thing will be much easier. But if not, Okay, that's fine. Let's consider. Okay. Let's see. And S be a subspace. So S, okay. Let's assume the basis S to be U1, U2, UK. Okay. In other words, we assume like the dimension of S is K. Okay. Okay. So here I'm telling you one process to build an orthogonal basis from a basis. Okay, so let's just take any of these bases. Okay, let's assume this one. Okay, so the first one is U1, right? Okay, so just take U1. Okay, the second one. Okay, if this is U1, this is U2. What I want is this one. Okay, so we know that U2 can be represented by its projection on U1 plus this orthogonal thing, right? Okay, so let me just use the U1 prime, okay, equal to U1. U2 prime to be U1, U2. This one minus this one. You get rid of this one. And the rest of the vector will be orthogonal to U1, right? Okay? So how do we get this part? This is a U1 dot U2, right? Okay, this will be U2, basically like this will be U1, U2, cosine theta, right? Right? So then this part will be U2, okay, the size of U2. This is this is U2. The size of U2, okay, times cosine theta, right? So this is what we want, right? So we just get like a U1 dot U2 divided by U1, right? And then, okay, we need to make it a vector. This one is not a vector. This one is a scalar, right? So we need to multiply the unit vector of U1, right? So you need to multiply U1 divided by U1, the size of U1, right? So this is the unit vector of this direction multiplied this scalar. This scalar represents like a U2 cosine theta, which is this amount, right? So the total together will be U2 minus, okay, U1 dot U2 divided by U1 square U1, right? Then we know like this one, inner product U2 prime, inner product U1 prime, what must be 0, right? Okay, must be 0. Okay, so this is like a U2 prime, and we can repeat the similar processes to continue, okay, getting, obviously like U1 prime, U2 prime, they are independent, right? Okay, I mean you can try to prove this by yourself, but basically like intuitively, I mean when I draw that geometry to you, I mean it should be obvious to you. Okay, and the U3 prime, it will be U3. You basically, this is like you can use something similar to this. Minus U1 dot U3. U3 dot, sorry, this is U1. U1 minus U1, U2 dot U3. U2. U2. Basically, you get rid of the projection, okay, the U3's projection on U1. You get rid of U3's projection on U2. The rest, okay, will be orthogonal to U1 and the U2. Okay, well, to be exact, the rest will be orthogonal to U1 prime and U2 prime. Okay, and you can continue doing this. And you will get an orthogonal basis. Okay, for any given basis, this is one way to construct the orthogonal base. Actually, we are going to discuss this like in a later section, but I think like because we are going to use orthogonal basis, so I will just describe the process here now. Okay, there's a term called Gram-Schmidt, process. Okay, to get this, but I mean, at the end of this chapter, but I'll just give you the head up. I mean, this is not very difficult to tell. Okay, you get rid of like the original projection on the previous vectors, then the rest will be orthogonal to the previous ones. I mean, basically, this is like a process you can continue doing. Okay, so that I mean this process allows you to get the orthogonal basis from from any basis. Okay, basically. Okay, so now, okay, so assuming that you have an orthogonal basis, now we can do that, right? Because like previously, I mean, if you say you don't know how to get an orthogonal basis, I don't blame you because we haven't talked about that yet. But now, I mean, we have a basis, and now I told you like how to get orthogonal basis from any basis. So now we have like orthogonal basis of S, just like I assume like the S is k-dimensional. This one is also k-dimensional. Okay. And then, okay, for any vector V in Rn, okay, any vector V in Rn, okay, that V1, okay, to be this one, okay. So this is actually the part that I got rid of, the projection, okay. You see, this is a V inner product W1 divided by the W1 is like the square of W1, right? This is exactly what I wrote here. This is a U1 dot U1, okay, times U1, okay, this W1 dot W1 times W1 plus blah, 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 this one. This we call this V1. And then, okay, V2 to be V minus V1. Because this V1 obviously is formed by W1 to WK, right? The the linear combination of W1 to Wk. So it means V1 comes from S1, right? V1 comes from, not S, V1 comes from S. V1 comes from S. Because W1 to Wk is the basis of S, right? And then, okay, the V2 equal to V minus V1. Okay, that's exactly just kind of like this one minus this, you know. So you can verify, okay, this V2, okay, must be perpendicular or like orthogonal, must be orthogonal to any of these vectors, W1, W2, W3, blah, 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 Wk. So V2 is orthogonal to any of these vectors. Just like what I show you, okay? This one is orthogonal to any of them, previous vectors, okay? I mean, for the similar reason. Okay? Then, so it tells you what? It tells you V2, okay, because V equal to V1 plus V2, and the V1 is in S, and the V2 comes from S, you know, orthogonal. Okay? So Rn is the direct sum of S and S orthogonal, because any vector in V in Rn, we can write it in this way, right? Okay? So that's a unique representation for, you know, for this V1 plus V2, where V1 comes from S, V2 comes from S, you know, orthogonal. So we know Rn must be, we can, according to the definition, Rn equal to S direct sum, S orthogonal. And then once we have that, the second one, you know, is a direct consequence, okay, from the first one, because like we have proved the property of that. So it can also prove that W1 to Wk is also a basis of S orthogonal. Yeah, I will leave that one for you. I mean, this is, it's kind of like the square matrix, the transpose of the square matrix equal to itself, right? This is not that difficult to see, okay? But I will leave this one to you, okay? So now we are, you know, in a position, okay, to talk about the projection, okay, the projection onto a subspace. Okay, first we have a definition like this. So that S be a subspace of Rn, okay, since Rn equal to S direct sum S orthogonal, okay, for any V in Rn, any vector in Rn, we have V equal to V1 plus V2 for some unique V1 in S and V2 in S orthogonal, right? This, we already know all this, okay, up to now, up to here, okay? Then we said the vector V1 to be the projection of V onto the subspace S. Okay, it should be projection, not project, okay? I mean, the projection of V onto the subspace S. If you draw it geometrically, it should be more obviously to, it should be more obvious to understand. If this is subspace, and you have a vector, this is a vector V, then, okay, the V is written in, okay, because this is V, this is V1, this is V2. V1 is in S. V2 is perpendicular or orthogonal to this subspace, right? So it's kind of like this. So, you know, if you draw it in a geometric manner, it will be obvious, okay, that V1 will be the projection of V onto this subspace S. Right? Right? Because now we are talking about Rn, right? So you can use R3 as as a way to visualize what we are talking about here. OK， 你可以用3次元，因为我们3次元以上没办法想嘛。那3次元至少我们都可以画得出来，对不对？所以3次元就大概是这样子。OK， 如果一个 subspace 就像一个平面嘛，对不对？那你把一个 vector 投影到这个平面，那然后它投影，在剩下来是不是就是垂直的嘛？对不对？所以跟那个平面垂直的，那就跟我这个一样啊。所以 V1 是在 S 里面 ，V2 是跟 S 垂直的，就是或者说你可以讲 V1 in S and V2 in S orthogonal， 对不对？对不对？所以我们可以把 V1 写成 PRO projection S。Okay, V. Okay, because V is projected to S. Okay, that's V1. Okay, so this is like a denotation. Okay, you need to remember. Okay. So then we have a theorem. Okay, V1 to Vk being orthonormal basis. Okay. So what is orthonormal basis? I already told you, from any basis we can create orthogonal basis, right? So orthonormal basis is that orthogonal basis, but we try to make each vector a unit vector, okay? Because they are already orthogonal to each other, right? 它们已经是互相都垂直了嘛，对不对？那我们只是把那个每一个在那个 basis 里面的那每一个 vector， 把它除掉自己的长度。就变成那个单位长，这个可以做吧？对，所以说我从这边先讲，你任何一个 basis 可以变成把它转换成 orthogonal basis， 然后任何一个 orthogonal basis 当然可以变成 orthonormal basis， 对不对？对不对？你只是把那个每一个 vector 除掉它们的长度而已，这很简单。好，所以说 So if V1 to Vk is an orthonormal basis for subspace S of Rn, then the projection V, so this V is any vector from not necessarily from this subspace. It could be from the original space. Or like the super space. Okay, so this V, okay, project V onto S will be V inner product V1 times V1 plus blah 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 blah. This is actually just like what we have here, right? So you may say, wait. So we have a denominator. 我们这边有个分母啊，那个分母怎么不见了？我刚前面是跟你讲说 V1， 你这个东西就是把 V1， 应该说把 V 这边的 V， 就是把它投影到这个W1 到 WK 这个那个 span 出来的这个 space 嘛，对不对？那你可能会问，那你可能问说，那这边。这个，你说这个跟前面那个跟后面那个有什么不一样？前面这边我们只假设 we only assume okay V W1 to WK is a orthogonal basis， 对不对？那下面这个东西是 orthonormal basis， 对不对？所以它的长度是1嘛，那长度是1就代表什么 ？W1 inner product W1 就是 norm 的平方是1嘛。所以这分母就都是1啊，所以说你就不用写，就这样子而已，其他没什么不一样。OK， 所以这个没什么特别好讲的哦。其实某种角度上来讲，这一块前面就讲过 ，We already talked about this. It's just like now we give it a name. to make it a little bit more formal, we give it a notation. OK， 可以吗？这样子应该都还可以接受嘛？好，然后再来就是比较好玩的 ，OK， 这个东西其实你们以前有在做过，只不过以前不是考虑在线性代数或矩阵上面去考虑这个东西啊，就是以前在那个你们在高中的时候不是常在做那种问题吗？就是说，给你一个3次空间上面一个平面，给你一个平面方程式，然后给你一个三次元空间上的任何一个点，问你这个点到这个就是在这个到这个平面的距离多远？你们在高中应该有做过这样的问题吧？这种问题至少我当年在做联考题目的时候，也在做这样的问题嘛。我想，台湾经过这么多年的演进，应该没有进展太多才对嘛，对不对？就是你们高中还是在学这一套东西嘛，对不对？就是空间上任何一个平面，空间上任何一个点，你到这个平面的距离是多少？因为我们讨论距离是讨论最短距离嘛，对不对？所以其实就是什么？就是刚刚这是要空间上一个点，然后你要求的就是这个跟它垂直的这一块嘛，就是假设这是个点，那你要求就是这个长度，就是个 distance， 对不对？对，就是或者我这样讲，如果这是把它想成这个点当一个 vector 的话，那你把这个 vector 减掉它的 projection， 剩下来就是这一块嘛。对不对？这一块的长度就是你要的，对不对？对不对？这个应该蛮容易理解嘛。你们高中都已经做过很多次了，对不对？对，所以我们这边讲 distance to a subspace， 当然我们之前说你说 subspace 不一定是一个平面啊，对，二次空间的 subspace 是一个平面没有错了，但是超过二次空间当然不是一个平面，但是用二次空间来这个我才画得出来嘛。就是再往上画不出来，但是直观的概念是一样的。直观概念 the intuition remains the same. Okay, remains the same. So basically, okay. So here, okay, let S be a subspace of Rn, and the V is any vector in Rn. Then for any U in S, and if U is not a projection of V onto S. Okay, then we have the size of V minus projection of V onto S. This size is what? This size is this one. The V minus this projection, right? So the size is exactly this. 就是这个垂直距离。It's going to be smaller or than V minus U. The size of V minus U， 这个应该，如果说我画图出来，就是你任何一个，因为 U 是什么 ？U 是任何一个在这个 subspace 嘛，就是我如果说随便画这个随便画一个这假设我这是 U 好了，那 V 减掉 U 就是这一块嘛，对不对？只要这个角度不是垂直的，它是不是一定不是最近的？对不对？从这个平面上任何其他的点到这个点，只要它不是垂直的，它一定比较远嘛，对不对？就是直观来讲的话，这个是很容易理解的，对不对？那当然，我们也要正嘛，我们要正，要怎么正 ？OK， 这个。就我们考虑这个东西，这就是 V 减 U，V 减 inner product， right？ 那这个东西会等于什么？这会等于这个乘 乘起来，这个乘起来，然后减掉。 Right? Okay. So the thing is, if you want to, what should I say? Minimize. If you want to minimize this, because this one is a fix, right? It's a must be positive, and you cannot reduce this because u, v are given, right? Okay, and this one is also positive. So the only thing is you can control is the angle between u and v, right? So if because this one, this u dot v, this is like it's a u v cosine theta, right? Right? So now, I mean, again, this one you have no control. You have no control, but you have control over the theta. So if the theta is 90 degree, or like the u and v are orthogonal or perpendicular, then this term vanish, right? This term vanish. That's when you have the smallest value of this, right? So that's the reason, okay, we are looking for, okay, the case that u and the v to be orthogonal. Okay, so if this is the v, this is let me see, v minus u. Yeah, so now let's look at this example. Okay, so if a vector is like this, and the S is it's a subspace spanned by these two vectors. I mean, actually, this is exactly what you have done in high school. Okay. Because 那个 subspace 就是一个平面嘛，两个 vector 展开来是一个平面，对不对？然后你这个 vector 你要到那边，所以 first you want to find the projection of v onto S. .所以031跟200它们是 orthogonal， 对不对？031跟200是 orthogonal， 它们两个 dot the inner product of these two vectors they are is 0, right? So these two vectors are orthogonal. You could make them orthonormal. I mean, basis. I mean, if you divide, I mean they're known like so it's like their known is it'll be 0, something like this, right? 对不对？第一个是这样子，对不对？就都平方加起来开根号嘛，对不对？339嘛，加1的平方1嘛，10开根号10根号10。我懒得把它弄得漂亮一点。另外200，那另外一个当然就更简单了，就100就好了，对不对？好不好？ 你可以这样子，你也可以就是按照我那时候前面讲的，就是你除上一个弄的平方，就看你自己要怎么弄 ，OK。然后你要 projection 就是按照这边这个，所以对不起，你的 v 是什么？113，所以这个 projection 这个 SV，OK 就会等于呢，按照这边前面写的，这是这边 v dot v1， 然后乘上 v1 加上 v dot v2， 这应该是这样写才对了。inner product 乘上 v2， 就这样子。That's it. So v is 113. So 113 dot this one, so it'll be 0, 1. So 就是出来根号16嘛 ，OK， 根号16，乘上 v1 plus, okay, and this one is 113 dot v2 is 1, okay, v2. So that's it. 那你这个自己加一下 ，v1 就是这个，这是 v1， 这是 v2， 就自己把它带进去弄一下。然后你 once you have the projection, then what you are looking for is like the v minus v1, and you get a norm of it. That's what we are trying to get for the shortest distance between v and the s. To be very honest with you, like if you say you skip my classes and you don't learn anything from this class, and if I give you this, I mean just from like a high school knowledge, you should be able to get it done. But of course, you are going to use something different, right? You may use some other technique that you learned from high school, but that's fine. I mean, as long as you can get the job done. But I really hope that you can pick up some concept from this class, OK？ 就是对啊，毕竟这门课我会希望你们从这边学一点东西哦，不是就是那个用高中的概念去做。高中的概念就是你得到那个，你可能用这两个先去做那个实现做那个平面出来嘛，那你有法向量，对不对？然后再弄一些有的没的。Okay. So another definition of projection. So this is, you see, this one is much similar to what we use, right? So this is what? This is like if W1 to WK is an orthogonal basis. So you see the projection become this. 那就是刚那个，因为前面是 orthonormal 嘛，所以这下面都是1。现在如果是 orthogonal， 就这下面就不保证是1嘛，所以说你要把这个下面分母写出来。You have to write down like the denotation, denominators. OK， 哦，对我刚 skip 这个，不好意思，回来一下。So if S is a subspace of all inner product space, and V is a vector in V, project V onto S, okay, called the projection of V onto S is a vector in S such that this one is minimum. So this is more like we are using like a geometry to define this thing. Okay, the previous one we are trying to the previous definition is because we already defined like a projection V onto S here. Okay, we already defined this one. But now, I mean, instead of providing this definition, this definition, we directly use like its property to define it. Okay, so geometrically speaking, Like that's like the shortest path is like something that's perpendicular to to that space. Okay, so this one I already talked about. So if B is U1, U2 to UK is an orthonormal basis, then this one is, because these two, the difference is that, I mean, orthonormal basis like the vector is of size 1. The size of the vector is of size 1, so you don't need to write down like this u1 dot u1 in the denominator. I mean, they are all 1 anyway. Okay, 这个前面都已经讲过了。So we are done with this section 2. Okay. So now, okay, the third section, okay, this square problem, okay. So it is kind of interesting because this square problem can also be considered as like the projection problem that we discussed earlier. Okay. So let A be a M times N matrix, and the B be a vector in Rn. Okay, so you have M rows, N columns. Okay, M times N matrices. Okay, and B be a vector in Rn. If B is not in column space of A, the system AX equal to B is with no solution. So throughout this class, I mean, at least, I mean, start from the very beginning, we try to talk about the system of linear equations, right? And later we try to write it down as like a matrix, okay? So basically, I mean, we usually represent it by something times x1 xn xm. Okay, equal to, this is a B. I just write B. Okay, right? Okay, B is also obviously also a column vector. Okay, so in reality, I mean, there are many ways you can consider this system of linear equation. I mean, one way to consider this is xn, sorry. Each of these vectors is of dimension n, right? This is n times n matrix, right? In other words, you have this system of linear equation has n equations, okay, and you have n unknowns, okay. So actually, okay, one way to think about this is actually if we try to represent each of these vectors v1, v2, vn, then what you are doing is x1 times v1 plus x2 dot v2 plus plus xn dot vn equal to b, right? It's actually any of these linear system of linear equation is actually like can be considered as like you are trying to do a linear combination of column vectors, right? So if B is so that pretty much implies that this column vector B has to be, you know, an element in the space spanned by these column vectors, right? In order for you to solve this system of linear equations, right? 就是说，你看哦，这如果说你把它理解成说，这个矩阵乘上一个 x 等于 b， 我们如果说把它理解成说，这个 b 事实上是可以被写成说这个矩阵的 column vector 的线性组合，这个大家可以接受嘛，对不对？如果不能接受，你们可能要再回去想一下，为什么这个是这样子。好，如果说是这样子，你们可以接受的话，那你们想一个事情，这是不是 imply 说你那个 b， 就是说那个右边那个 b 那个 column vector， 一定是要出现在你的那个矩阵的那个 column space。什么叫 column space？ 就是用那些 column vector 就是 span 出来的 space， 你才可能这个矩阵才有解嘛，这个线性方程组才有解嘛，要不然的话你没办法解，对不对？对不对？对，因为它其实就是一个这个 b， 其实我们就是想要把这个 b 写成这个 v1 到 vn 的一个线性组合。那这个 x1、x2、x3 一直到 xn， 其实就是怎么样子就把这个 column vector 线性组合起来，让它变成 b 嘛，对不对？那你现在如果说 b 不是在它的那个 column space， 那你根本没有可能做到这件事情嘛，对不对？对，所以第一句话就是说 ，if b is not in the column space of A, the system AX equal to B is with no solution. You have to understand this sentence first. 好，那接下来下一个问题就是，你想要找一个 solution， 这个 solution 是什么东西呢？这个 solution 这个 x 是让 AX 它会等一个 B prime， 这个 B prime 跟 B 之间的距离是最小的。我们希望做到这件事。其实呢，我们在做什么事情？我把它讲得更简单一点，就是如果你把 column space 想成一个 column space 是一个 subspace 嘛，对不对 ？column space 是一个 subspace， 那其实就是你希望找到这个 B 到这个 subspace 最近的距离嘛，对不对？那这不是我们刚刚前面那个讨论老半天的那个东西吗？对不对？所以你其实要去找什么 ？B 到这个 column space 的一个 projection。OK， 然后再点。对，那我们现在先休息一下，我们回来继续讲，好不好 ？OK。